So welcome back, students. In the previous video we talked about diamagnetism and paramagnetism. In this video we will talk about ferromagnetism. What is ferromagnetism? Ferromagnetism means the nature of a material to be attracted to a magnet very strongly. What you see as magnets in your life, they are all ferromagnetic materials. When we talked about paramagnetic materials, we said something similar. We said paramagnetic materials are attracted to a magnet, and ferromagnetic materials are also attracted to a magnet. Then what is the difference between paramagnetic materials and the ferromagnetic materials? The difference is that the ferromagnetic materials are attracted to a magnet very strongly. There is a very strong attraction that takes place in the case of ferromagnetic materials when you bring them near a magnet. But paramagnetic materials are attracted but not that strongly. So that is the difference between ferromagnetic materials and paramagnetic materials. The name ferromagnetism suggests that it has something to do with iron, because ferrum means iron. But iron is not the only material that exhibits ferromagnetism. Cobalt, nickel and gadolinium are some other elements which exhibit ferromagnetism. And some alloys like alnico, they exhibit ferromagnetism. Alnico is an alloy made of aluminum, nickel and cobalt, and it exhibits ferromagnetism. So what is different about this ferromagnetism when you compare that with paramagnetism? To understand it, we need to first look at the element iron. The element iron has the atomic number 26. So it is Fe26. What is the electronic configuration of iron? We'll do it now. So I have 1s2, then 2s2, 2p6, 3s2, 3p6, 3d10, then 4s2, 4p6, 4d10 and 4f14. It goes on like that. Let us see the electronic configuration for iron. So it will be 1s2, 2 electrons gone, then 2s2, and say 1s2, 2s2, and then 2p6 and 3s2, and now 3p6 and 4s2. So 3p6 and 4s2. And let us see how many electrons have we accounted for. 2, 4, 10, 12, 18, 20. So you need 6 more to reach the number 26. So here you wouldn't have, so you have to come to the 3D orbital, but then you can't have all the 10, you can only have 6. 3d6. So this is going to be 3d6. So this is the electronic configuration of iron. Notice that 1s2 is paired, 2s2 is paired, 2p6 all the electrons are paired, 3s2 paired, 3p6 all the electrons are paired, 4s2 both electrons are paired. And when it comes to 3d6, let us see how it's going to look like. Okay, so this is a 3D orbital, 3D6. So I have 1, 2, 3, 4, 5, and then 6. You notice that there is only one pair of electrons in the 3D orbital, and there are 4 unpaired electrons in the 3D orbital for iron, which means that this electron will have a magnetic dipole moment, this will have dipole moment, and all the 4 electrons will have dipole moment, and the atom, the iron atom, will have a net dipole moment. So the iron atom has a net dipole moment, like a paramagnetic material. The paramagnetic material too, like aluminum, you had a net dipole moment in the atom. The difference between a paramagnetic material and the ferromagnetic material is that in the case of a ferromagnetic material, there is a strong interaction among the atoms. The magnetic fields of the atoms strongly interact. So what happens is that they are, if you take a paramagnetic material, the magnetic fields of these atoms are locally aligned. What was happening in the case of paramagnetic material? Even though individual atoms had magnetic dipole moments, the temperature made those atoms to move chaotically. Okay, so there was no net magnetic field in the case of paramagnetic materials. But in the paramagnetic materials. But in the case of ferromagnetic materials, what happens is that because of the strong interaction of the atoms, in a very small area, which you call as a domain, which is a very small volume, these the atoms align to produce a net magnetic moment. Okay, so I'll say this could be one domain. So the atoms in that domain, in that small volume, they align to give you a net magnetic moment. So this could be something else, and this magnetic moment could be like that. In this domain, there is a net magnetic moment, but that may not be the same as this one. So likewise, we have something else and something like this. So you have a net magnetic moment. So locally there is a net magnetic moment, and what will be the size of it? Like if you look at the domain, it could be 1 millimeter wide. So in that volume, that 1 millimeter volume, then all the atoms could be aligned to produce a net magnetic moment. But notice here, but then if you take a reasonably sized, a big iron piece, then all these magnetic moments will produce no net field, even in this case. Even though each domain has a net magnetic field, they are randomly arranged in all those different domains, so you wouldn't still get a net magnetic field outside the ferromagnetic material. But what will happen if I take this material and place it in an external magnetic field? Then clearly all these things will try to align to the applied magnetic field. So you see that when this magnetic field is applied like this, all these domains, will try to align like this. Maybe something like this. There is a slight change, but they will try to align. So the stronger the magnetic field, then the greater the alignment would be. But you see, all these domains will naturally align like this. So now this material gets magnetized, and it is very strong, quite unlike the paramagnetic material. This magnetic field will be very strong, because in the case of paramagnetic material, the magnetism was fighting against the temperature. The external magnetic field was trying to hold those atoms against the temperature, because the atoms are moving like in random directions. So the external magnetic field was trying to align all those atoms. So it was a little difficult in the case of paramagnets. But in the case of ferromagnets, it's easy because they're locally aligned. So now it's only a question of aligning them to the external magnetic field. So temperature doesn't play too much of a role here until the temperature reaches really high value. The normal temperature ranges, you don't have to deal with temperature. The external magnetic field doesn't have to deal with the effects of temperature. If the temperatures are restricted to a manageable range. So it is very easy to align them, because the interaction among the atoms themselves take care of the temperature to a large extent. But notice that temperature will still play a role, which we'll talk about a little later. But under normal circumstances, you can expect not to worry about the temperature. The domains will kind of take care of the temperature effects. But that is not true in the case of ferromagnets. Why do the domains take care? Because of the strong interaction among the atoms of a ferromagnetic material. That kind of strong interaction is not there in paramagnetic materials. Even though both of them are attracted by magnets, the difference is that in the case of ferromagnetic materials, there is a strong interaction among atoms which will align them very easily. In the case of paramagnetic materials, that is not the case. There is not too much of an interaction among atoms in the paramagnetic materials. That is why you have to contend with the temperature. So the temperature tries to move those things in the case of paramagnetic materials, the atoms, and you are trying to align the atoms against the temperature. So that effect is less. But here you don't have to contend with that. So you can align these atoms very easily in the presence of an external magnetic field. I want to give you a demonstration. I have a magnet here. So I have two pieces. Okay. So now you can see that they are not touching each other. They are not touching each other now. Okay. They are not attracted to each other. I should say that. Attracted to each other. But if I take this magnet and one of the pieces is getting attracted to the magnet now. And now watch this piece, and if I keep it here, see, notice that this piece is attracting this. Why? Notice the field due to the magnet is not much strong here. If it was stronger than this piece, the magnetic field due to this piece, then this would have automatically gone and stuck there. But the notice here, if we keep it here, at this point, the field due to this is slightly less than the field due to this one. So because this is magnetized, this piece is magnetized. So I am keeping it here, now it is able to attract this piece. So these two are ferromagnetic materials. So they get attracted to magnets. And this has got attracted to this, and now this has got attracted to this piece. Very easy. Okay? And notice here, if let's see, if I've got a bell pin also here. So notice here, I'm going to remove the magnet. Notice that the bell pin is getting stuck to the piece now. So even though the magnetic field is removed, notice that this is partially magnetized. May not be fully, but then there is still a partial magnetism. It is able to retain the magnetic field at least slightly. Okay? So materials like this, which retain the magnetism after they are magnetized by a magnet, and the magnet is removed, such materials are called as hard magnets, or this is called as hard ferromagnetism. And materials which do not retain the magnetism after the magnet is removed are called as soft magnets or soft ion magnets. And that is the reason you are using soft ion core in electric instruments. Once the magnetism is removed, meaning the current in the coil is stopped, you don't want the core to retain the magnetism. So you have to use soft ion materials there. Soft ion materials won't retain the magnetism once you remove the magnetic field. But hard ion materials will retain the magnetism. That is the difference. So from now on, you know what it means to call something as soft ion core. So the core of the instrument, the material you use as a core for the instrument, will not retain magnetism. So it is soft ion. If it retains magnetism, then it is hard ion. So that is the difference between those two. And in the case of ferromagnetic materials, the permeability, μr, is very, very high. It could be in thousands basically. It could be more than 1,000. It could be in hundreds. It can be more than 1,000. The relative permeability. But that is not the case with paramagnetic materials. It was slightly more than 1.00001 or something. Okay, 1 in 1 lakh in the case of paramagnetism. But in the case of ferromagnetism, the relative permeability μr could be in hundreds or more than 1,000. It's high. And the susceptibility xi is almost equal to the permeability in this case. In the case of ferromagnetic materials, susceptibility is not very small, it is huge. We saw this. What does relative permeability μr? μr is equal to 1 plus xi. This is the susceptibility. And this is the relative permeability. So, in the case of ferromagnetic materials, this could be more than 1,000. So, this could be more than 1,000 actually. So, this is 1 plus xi So this is almost equal to mu r because 1 can be ignored. So you can say that in the case of ferromagnetic materials, okay, mu r is approximately equal to Z. The relative permeability is almost equal to the susceptibility in the case of ferromagnetic materials. But in the case of paramagnetic materials, that was not what was happening, because Xi value in the case of paramagnetic materials was 0.00001. It's 10 power minus 5. So it is very, very small value in the case of paramagnetic materials, but it's very high in the case of ferromagnetic materials, and that is because of this domain effect. And the domain effect is because of the strong interaction among the atoms of a ferromagnetic materials. They can influence one another very easily. The ferromagnetic atoms can influence one another very easily. So they can align themselves and form domains. So that's the key point when it comes to ferromagnetic materials. Hope this is clear to you. Now let us talk about the temperature effect on ferromagnetic materials. When we talked about paramagnetic materials, we said the magnetization was proportional to the applied external field and was inversely proportional to the temperature. Because the temperature is high, then the atoms of the paramagnetic material would be moving much more vigorously, so it will be difficult to align them to produce a net magnetic field. So you need much bigger external magnetic fields to produce the same effect. So we said that finally the susceptibility was equal to the Curie constant by temperature mu naught. This is what we said for paramagnetic materials. So we said if the temperature increased, then the susceptibility was less, because it's difficult to control atoms which are jiggling and moving with a lot of energy. Can that happen in the case of ferromagnetic materials? Well, under normal temperatures or over a long range of temperatures, it doesn't happen, because the interatomic influence, the interaction among atoms to align the dipole moments of the individual atoms and to create a domain, that is very strong at lower temperatures. But if we keep increasing the temperature of a ferromagnetic material, then there comes a point where the temperature effect will overrule the interatomic interaction. The atoms in a ferromagnetic material also will behave more chaotically. They will be jiggling much more vigorously and moving, and it is difficult for an external magnetic field to align. But then that happens only after a certain temperature. Till that temperature, the interatomic influence overrules the temperature effects. But then you keep increasing the temperature more and more, then at some point, then that effect, the temperature effects, will overtake, and the ferromagnetic material will cease to be a ferromagnetic material but will become a paramagnetic material. So if I take iron, which is a ferromagnetic material, and if I keep heating it, if I keep increasing the temperature, then at 1034 Kelvin, iron ceases to be a ferromagnetic material and it becomes a paramagnetic material. And this temperature for iron, this temperature is called as the Curie temperature, Tc, the Curie temperature. So, the Curie temperature for a material is the temperature at which a ferromagnetic material will cease to be a ferromagnetic material but will become a paramagnetic material. But below this temperature, it would be a ferromagnetic material with very high susceptibility and relative permeability. But once it becomes a paramagnetic material, then the susceptibility will come down. It will be a very, very small number because the temperature effect overtakes the interatomic influence of this material. And this is for iron. For cobalt, this is somewhere around 1400 Kelvin. So that is the Curie temperature for cobalt. And what is interesting is gadolinium. This has a Curie temperature of about 292 Kelvin. I think your book says it's 317. Let's say it's somewhere around 300. Okay. Other sources say that the Curie temperature for gadolinium is 292 Kelvin. So what does it mean? It's Kelvin. If you convert that into Celsius, then it's going to be 273. Yeah, 300 minus 273. So what do you get? It's going to be about 27 degrees Celsius. So somewhere around, I'll take this to be 300 Kelvin. 300 Kelvin, that's about 27 degrees Celsius. So till 27 degrees Celsius, gadolinium will act as a ferromagnetic material. It will have a strong attraction to a magnet. But beyond this temperature, it will become a paramagnetic material. So in room temperature, gadolinium is a ferromagnetic material. And then if you just take it out, if you just heat it slightly, then it becomes a paramagnetic material. It will still be attracted to a magnet, but then not so much. There is a very weak attraction. So it becomes a paramagnetic material. So they jokingly say, if you take gadolinium, it would be a ferromagnetic material in winter and a paramagnetic material in summer. So it depends on the month. So in November, December, it's going to be a ferromagnetic material, but in June, July, it will be a paramagnetic material. So that's the joke about it. Anyway, so what you need to understand here is that if you take a ferromagnetic material and if you increase the temperature of the material, you will reach a certain temperature at which this will cease to be a ferromagnetic material, but then it will become a paramagnetic material. And once it becomes a paramagnetic material, then the susceptibility Xi will have very small value. So Xi will have very small value. This paramagnetic, it will be in hundreds, it will be in more than 1,000. But then when it becomes paramagnetic, it will be 0.0001, 0.002. It's a very small number. Okay? So this is given at that time. Once it becomes paramagnetic, then the susceptibility is given by this equation. C by constant divided by T minus Tc. So if you heat it to say 1500 kelvins, then 1500 minus 1400 will be that C by 100 would be your magnetic susceptibility. So this is a very important equation. So this is for ferromagnetic materials. But less than that, you don't have to worry. Okay? If it is 1000 instead of 1400, so let's say it's 1000 Kelvin, then it doesn't even apply. This is applicable only when it becomes a ferromagnetic material. As long as it remains as a ferromagnetic material, this doesn't apply to it. But once it becomes a paramagnetic material, then if you want to find the susceptibility of the material at that temperature, you can find it like this. There is a table given in your textbook, and I want you to go through the table and find the different temperatures at which different materials will go from ferromagnetism to paramagnetism. We look at the table. It's a very interesting table. Now let's do the example problem 5.11. Let me read the problem first and then go on to do it. A domain in ferromagnetic iron is in the form of a cube of side length 1 micrometer. Estimate the number of iron atoms in the domain and the maximum possible dipole moment and magnetization. That's the question. Then the given data are the molecular mass of iron is 55 grams per mole, and then density of iron is 7.9 grams per centimeter cube, and then each atom has a dipole moment of 9.27 into 10 power minus 24 ampere meter squared. So using this data, you are supposed to find the number of iron atoms in that cube, in that domain, and the maximum possible dipole moment and magnetization. So maximum possible magnetization. So these three things you are supposed to find. Okay. Then how do we do that? First of all, it's like if you have material like this, you'll have many domains. So this is one such domain. Okay. So they're given you like 1 micrometer side. So it's a cube. And in that cube, how many atoms are there? To do it, I'm going to make use of this bit of information and this bit of information. I'm going to take the density of iron. The density is 7.9 gram per centimeter cube. And I know the volume, and from the volume I can find the mass, and if I have the mass, then I can find the number of atoms in the mass. We'll do it now. So what's the volume now? So the volume is equal to 1 micrometer whole cube, 1 into 10 power minus 6 the whole cube. So that is meter cube. So that is equal to 1 into 10 power minus 18 meter cube. But rather than using meter cube, if I have this in centimeter cube, then I can get the mass in grams quickly. So let me do that in centimeter. So 1 micrometer is actually 1 into 10 power minus 4 centimeter. So this cube and this cube is going to give me 1 into 10 power minus 12 centimeter cube. So that is the volume. 1 into 10 power minus 12 centimeter cube is the volume of the domain. Okay. So then what is the mass of the domain? So the mass of the domain M is rho times the volume. So that is going to be 7.9 gram per centimeter cube, multiplied by 1 into 10 power minus 12 centimeter cube. So centimeter cube and centimeter cube will cancel. So the mass is given by 7.9 into 10 power minus 12 grams. So this is the mass. Okay. So in this mass of iron, how many iron atoms are there? I'm going to use this piece of information to get that. What do we know? The molecular mass is 50 grams per mole, which means that 1 mole of iron weighs 55 grams. So 55 grams. So 55 grams. Let's see, like number of atoms in 55 gram of iron is equal to 1 mole, right? That is 6.023 into 10 power 23. So many atoms are there in 55 grams. And how many atoms are there in 7.9 into 10 power minus 12 grams? So then you can say the number of atoms in 7.9 into 10 power minus 12 gram is equal to 6.023 into 10 power 23 is divided by 55 multiplied by 7.9 into 10 power minus 12. So this is going to give me 8.65 into 10 power 10. So this will be 8.65 into 10 to the power 10. So the number of atoms in the domain is this. So once you know the number of atoms in the domain, what would be the maximum dipole moment? If you add all the dipole moments, if all the dipole moments are aligned perfectly, then that would be the dipole moment, the maximum dipole moment of the domain. So the maximum dipole moment, we call this as M max, is equal to number of atoms in the domain into the dipole moment for each atom. So that is M. Call that. Okay. So I am just putting a vector here just to differentiate this M from this M. This is mass and this is dipole moment. So that is why I am using it. I am not bothered about the vector per se. I am worried only about the magnitude of it. But I am putting this vector just to differentiate between this M and that M. That's all. So this would be 8.65 into 10 power 10 multiplied by 9.27 into 10 power minus 24. Okay. So ampere meter squared. So this is going to give me 8 into 10 power minus 30. So this is going to give me 8.0 into 10 power minus 13 ampere meter squared. So this is the maximum dipole moment for that domain. And what about magnetization? We know the magnetization is the dipole moment per unit volume. So I have this, and if I divide that by the volume, then I should get the magnetization. So magnetization is M is equal to, this is maximum magnetization. So M max is equal to the maximum dipole moments by volume. So that is equal to 8.0 into 10 power minus 3 ampere meter squared divided by 1 into 10 power minus 18 meter cube. So this will be that. So this will give you 8.0 into 10 power 5 ampere per meter. So the maximum magnetization is equal to 8.0 into 10 power 5 ampere per meter. So this is how you do this problem.